Okay, for today we're going to get into lesson 4.2 in BC Calculus. We're going to be talking about two very important theorems, Rolle's theorem and the mean value theorem. And look here at the top of the screen, this symbol, the backwards E, you'll see that come up from time to time. It means there exists. There exists. Mathematicians use that symbol occasionally. Why do I bring that up? You're going to see it highlighted in Rolle's theorem. Rolle's theorem says that three conditions must be met. One, if f is a continuous function on a closed interval from a to b. That's our first condition. And number two, the function is differentiable on an open interval from a to b. What does it mean to be differentiable? It means our derivative exists. That means our derivative would never have non-existence. We won't have corners, cusps, vertical tangent lines, anything like that. So if your function is continuous on the closed interval, differentiable on the open, and here's our third condition, if at the endpoints f of a equals f of b, then, provided that these three conditions are met, then here is this backwards E. There exists a C. Here's the element of symbol. That's that almost looking like the Greek letter epsilon. It's looking like an element. It belongs to the open set A to B such that f prime of C equals 0. What this theorem is really saying is if your function's continuous, if the derivatives exist everywhere on the open interval, and if f of a equals f of b, then there is some x value, we'll call it c, such that when we take the derivative at c, we'll get 0. Remember, a derivative is representing the slope of a tangent line. Take a look at the second picture. Our function is continuous on that closed interval. No corners, no cusps, no vertical tangent lines. Our derivative would exist everywhere on the open interval. And let's also assume that whatever f of a is, that's also what f of b is. There will exist some x value. There might be more than one. That's what I'm trying to show you on the second picture. Where the slope of that tangent line at that particular x value will equal 0. So that's Rolle's theorem. Meet those three conditions and you will be able to find an x value such that f prime of c, f prime at that x value is 0. Let's real quickly take a look at example 1. Let's just say that we have f of x is equal to x cubed over 3 minus 3x on the closed interval from -3 to 3. First of all, show that f satisfies the hypothesis of Rolle's theorem. That means the three conditions. And then find that c value. We're saying there exists a c. Let's actually go further and find that c value such that the derivative at that c value is 0. So, how do we show f is continuous? Here's a wonderful shortcut. F is a polynomial, and polynomials are continuous everywhere. So that's wonderful. If you can make note of having a polynomial, you're going to be able to say that your function is continuous on any closed interval. Second of all, f being a polynomial is also differentiable everywhere. So that's wonderful. So if we don't have a polynomial, we're going to have to make mention about where the function might be discontinuous and pay attention to that. But thankfully, a lot of times we are given a polynomial to work with. Well, the third condition of Rolle's theorem, you can see it up at the top of the screen. We need to check the endpoints, find out what f of -3 is. Well, f of -3, if I plug -3 in, -3 cubed is -27. -27 over 3 is -9. And negative 3 times negative 3 is positive 9. So this f of negative 3 is equal to 0. If you substitute in f of 3, you would quickly find that 3 cubed is 27. 27 over 3 is 9. 3 times 3 is 9. This would also be 0. So I can say f of 3 equals f of negative 3. I do want to point out very, very, very importantly, this is so important, that for Rolle's theorem to be true, we're not requiring that these y values must equal 0. You can see in the original picture that I had here, my f of a and f of b, it could be some positive y values. We could have dropped it down. We could have had y values that were negative just as well. It's just coincidence here that these y values are 0. More importantly, these y values at the endpoints are in agreement. So what we can now say is, so there exists a c such that f prime of c equals 0. Well, let's find f prime of x. F prime of x, taking the derivative with respect to x, bring down your 3, and the 3 and the 1/3 cancel, and you'll just have x squared, and then the derivative of negative 3x is simply minus 3. So f prime of c, we're saying there's some number, c, x value, such that c squared minus 3 is our tangent line slope, but I'm going to say this should arrive at 0 somewhere according to Rolle's theorem. So if I add a 3 to both sides, c squared's equal to 3. C would be plus or minus radical 3. Now radical 3 is about 1.73. So show that f satisfies the hypothesis of Rolle's theorem. Find all the c value on that open interval such that f prime of c equals 0. Well, here it is. And this is by Rolle's theorem. We know this to be true. Now let's take a look at this next example. Let's say that we have f of x equals 1 minus the absolute value of x. This is the opposite of the absolute value of x plus 1. So our graph is an upside down absolute value graph. It would look something like that. And we're only going to be looking at that between negative 1 to 1. Does Rolle's theorem guarantee that there is some c value such that f prime of c equals 0 here? Well, we would have to go through our checklist. We'd say, well, is f continuous on that interval? We could quickly say that it is. And really we could even go back to the definition of continuity to prove that, to show that everywhere on that interval f exists for any given x value there. The limit would exist for that x value and they'd be in agreement. But here's the problem. F prime of 0 does not exist. We have a corner there. So Rolle's theorem does not guarantee that the derivative must equal 0 for some value of c on that open interval. So even though the third condition is met too, I think it's important for us to realize the third condition, f of 1 would equal f of negative 1. Both of those would equal 0 if you really think about it. The fact is, once you fail one of those 3 hypotheses, one of those 3 criteria, the game's over for using Rolle's theorem. We can't guarantee that that's going to hold true. Okay, so real quickly, let's go to the mean value theorem. The mean value theorem is incredibly important, super important. It's actually covering Rolle's theorem. Rolle's theorem is actually just a very special case of the mean value theorem. So the mean value theorem is the big idea of today. It's our major learning target. So if f is continuous on a closed interval and it's differentiable on an open interval, we don't even have a third condition here, then there exists a c on that open interval such that f prime of c equals f of b minus f of a all over b minus a. I hope you remember f of b minus f of a all over b minus a is an average rate of change. It's just the slope formula, guys. It's your y2 minus y1 all over x2 minus x1. It's also the slope of a secant line. By way of comparison, if we were to look at f prime of c, f prime of c is saying that we have an instantaneous rate of change. Forgot the t there. So it's an instantaneous rate of change. It's also the slope of the tangent line. So what we're really seeing here is this, that if your function is continuous on a closed interval and differentiable on an open interval, then there will be some x value such that the instantaneous rate of change at that x value would equal the average rate of change on that interval. Also, the slope of the tangent line would have to be equivalent to the slope of the secant line for somewhere on that interval. Let's get a picture to see this. As you can see geometrically right down here, the mean value theorem says somewhere between x equals a and x equals b, the curve has at least one tangent line parallel to the secant line from x equals a to x equals b. Remember, the secant line will just connect those 2 points at x equals a and x equals b. But the tangent line, you can see real quickly, would have the same slope. That's what it means to be parallel. And I have an alternate form right over here. Really just the same exact kind of a picture. Well, my goodness, this next example is incredibly important, very important on the AP exam. And we need to be very, very careful to talk through this. Very easy to miss this question in particular. So let's take it slow. Let's say f is defined to be x plus 1 over x. It's on a closed interval from 1 over 2, comma 2, 1/2 to 2. Show that f satisfies the 2 conditions of the mean value theorem, and then find all c in that open interval satisfying the conclusion. Well, the first question is f continuous on that closed interval? Just want to make a quick comment. F is only discontinuous at x equals 0. So f is continuous on the closed interval. So that's our first condition. That's good. The second condition, well, we need to take a look at the derivative. Well, remember, 1 over x is really x to the negative 1. And if we took a derivative here, f prime of x, we'd see that we'd have 1. And remember, the derivative of x to the negative 1 would be minus 1 over x squared. This derivative exists everywhere except at x equals 0. That means f is differentiable on the open interval from 1/2 to 2. So where are we headed with this? Well,